everyone. Welcome to another edition of the ARENA virtual seminar series. Today, our speaker is Aaron Couture. It's my pleasure to introduce him today. So Aaron's an experimental nuclear physicist at Los Alamos National Laboratory. He got his bachelor's and PhD from University of Notre Dame. He first started off falling in love with physics when he was an undergrad. Getting to assemble old particle accelerators and getting his hands dirty with those things. So for his PhD, he worked on direct measurements of reactions with the CNO cycle with one of his old accelerators that he worked on, as well as neutron capture work with the NTOF facility at CERN. So after that, he moved to Los Alamos National Laboratory in 2006 to work at the Lano Neutron Science Center, LANCE, where he studied neutron capture by hook or by crook for nuclear astrophysics, and also for societal applications ever since. With that, take it away, Aaron. Thank you.
All right, so thank you very much. Hopefully everyone can see my screen and hear me. If there's any issues with that, please just let me know. I'm happy to take questions during the talk, but someone might have to tell me if there's a raised hand or something like that, because I may not notice right away. Yeah, so I'm really happy to have a chance to talk with you about some of the work that we've been doing at Los Alamos and sort of where things are going in terms of neutron-induced reactions. To sort of start that, okay. I want to say a few words about neutrons and just sort of introduce them, and then say a few words about why study neutron and neutron-induced reactions, and then give a few updates on some measurements that have been performed for the S process. And then after that, I'll talk a little bit about the facilities and how we're trying to do these measurements. There'll be a whole swath of things in terms of neutron-induced nucleosynthesis that I'll miss in the course of that, and that is sort of the inevitable result of trying to make a couple of choices and keep things to a time that we can all have an interesting discussion, but not be trapped forever. So just to sort of at a most simple level orient things, one of the things I like to do is start off, most people have taken time to look at a table of the elements and sort of say something about what are the elements we see and their many different properties. And so you have things like hydrogen and helium up at the top, and then you get down to the ones that nobody knows about that are like the lanthanums and the ceriums and the praseodymiums, or the uraniums, neptuniums, and plutoniums down at the bottom. But it's a way of laying these things out that tells us something about the behavior of these elements, how they behave chemically, and maybe some things about where we see them. Now, from a nuclear physics perspective, this gives us part of the picture, but I would say that it doesn't really fill things in. And so as a nuclear physicist, what we often try to do is take this chart and add an extra dimension to it. And so we'll lay things out in this sort of a direction, where if you were to look at this large, what we call chart of the nuclei, and this is what I would call a nuclear physicist's view of the landscape, as you go up, so as you move vertically, you add protons. So each row here would be one of the elements in that table of the elements. And as you look at columns, you take the same elements, but you change the number of neutrons. And how these things evolve as a function of this really is what we're trying to study in low-energy nuclear physics, and it has really important consequences for nuclear astrophysics and for how we find elements in our cosmos. And where they might things might be aligned in the table of the elements from a chemical point of view based on the column that they sit in the table of the isotopes, or chart of the nuclides, they all fall along magic numbers that maybe don't look to have laid themselves out quite so well, but you see these red lines put in. And this is where there's a particular configuration of nuclei that's particularly stable, where they sort of like this nuclear configuration for a variety of reasons. And we see those effects directly in the observed abundances of the elements. You also, so the black squares here, as you're sort of going up, are the stable isotopes. And there's a lot of other things indicated on here that I'm not going to go into, but you might see that here you get sort of toward the end, and there's this whole region where there's no more stable isotopes until we get out to the things like uranium and plutonium, which aren't completely stable, but they live for an awfully long time. And so even understanding how do these gaps appear is part of what we're trying to understand in nuclear physics. But I said we're going to do all of this with neutrons. Neutrons don't even make it onto the table of the elements. Here we've zoomed into the very bottom left corner of that chart before, and you have this neutron. So the lifetime of the neutron is about 870 seconds. We know some things like its mass. It's not charged. There are no protons involved in it. It's a spin 1/2 particle, so it's a fermion-like particle. And if you really want to get into the details of everything about a neutron, you can read 16 more pages in the particle data book. I won't bore everyone with that, but this is sort of what's driving these reactions. And these different properties, like the lifetime, the mass, and the charge, really are important for how these reactions take place. Let's see, yeah. So what are the types of nuclear physics that we can do with these neutrons? So, I mean, one thing we can do is studies of the weak force are done because it's a, quote, simple nuclear system. It has a single nucleon as opposed to trying to do this in a larger nucleus. It has a lot of implications we're going to talk about today for nuclear astrophysics. From a nuclear physics perspective, neutron resonances and nuclear structure are important. You can use neutrons as a probe because they're uncharged to get inside of something and look at what's going on the inside to do imaging. It's one of many examples of physics applications coming out of the nuclear physics. And then another opportunity is in the studies of fission, which sort of make all of these different pieces of physics hopefully behave at the same time. Okay, but today we're talking about the nuclear astrophysics portion of things for ARENA. And so we took that chart that showed all of these different nuclei in terms of how, from a nuclear physics perspective, they can be configured. But another way we can look at it is what do we actually see if we look out in the cosmos? So here I've plotted, and first of all, you'll note that the vertical scale is a logarithmic scale. So the abundances are ranging from 10 to the -4 all the way up to 10 to the 10. So that's 14 orders of magnitude in variation. These are what I would call traditional astronomers' units, where silicon is 10 to the 6. This was chosen for a reason, and I can't comment on why today, or any other day, actually. But this is sort of the default scale that was set up for this. But what we see is we go up in atomic mass. In some sense, this is increasing in element, but it's really about what's the total mass. The low mass elements are made through charged particle reactions in stellar burning. Stars actually burn these elements, they create energy out of them, and then they build up heavier and heavier elements from these reactions. But we get to a point where fusing two charged particles together no longer generates energy. When we get to that point where it no longer generates energy, what that means is this can't be used to support a star anymore. So all of these elements to the right of this red set of arrows have to be made through another process. Some of this is sort of indicated conceptually by the fact that their abundances are much lower. So somehow these natural processes that take place to make these lighter isotopes that are through stellar burning, something else has to be going on. And what's driving the production of all of these elements, basically starting at iron, are neutron-induced reactions. There are two major neutron processes called the slow neutron capture process and the rapid neutron capture process. We'll refer to them as the S and the R process throughout the rest of the talk. And they each contribute about half to the abundances of the heavy elements. And you can see that the blue dots are things made through an S process. Red dots are things made through an R process, at least how it was deconvolved in the late 80s. And they generally make many of the same elements or isotopes, but in different abundances. And so you could see, for example, here there's a peak, and most of this abundance is attributed to the R process, while there's another peak later on that's largely attributed to the S process. Okay? One of the issues with this, we talked about slow and rapid production of the elements. So the slow neutron capture process takes place closer to stability, and we're going to talk about specific reactions that have been measured for the slow process. So this is much better studied experimentally. And so in fact, many, many times, if you hear someone talk about an R process abundance, and that's certainly true for what I'm showing today, this is actually what is sometimes known as an S process residual, okay? And what that means is that you look at what you actually see across all of the elements, you subtract what your models and your measurements say you can make through an S process, and then say the rest of it must be made through an R process. So getting these different details right, even for something like the S process where we might claim it's better known, really has significant impact, because otherwise your R process modeling is trying to reach a goal where there isn't even, you might be trying to reach the wrong target, okay? So this is sort of the breakdown of what we see when we look out in the cosmos and where we are today in terms of trying to break these into different processes to make them. And I've indicated here as well some of the places where these processes might be taking place. So the next piece that I'm going to talk about in a little bit more detail is what's called the weak S process. It's responsible for production in the mass 60 to 90 regime. Primarily, it operates in massive stars, so about 8 solar masses and above. And what's driving this is core helium burning and shell carbon burning. And so if we understand what's going into this, it can tell us something about these processes. Now, what's wrong with the weak S process? So in about 2005, there was a newly published result of nickel-62. And the cross-section, or here I've called it MAX, for Maxwellian average cross-section, I should have written that out, I apologize, went from 12.5 millibarns to 28 millibarns. This was a case where the expected uncertainty was about 30%, as you can see from this 12.5, plus or minus 4. And instead, it more than doubled. This was based on a new activation measurement. And then when this was folded in to a stellar model of what was going on, not only did your nickel abundances change, but the abundances of about 30 elements downstream all also changed. So you can see that here the germaniums and the arsenics, the bromines and seleniums are all being increased by almost 40%. Okay? So this is a huge impact on what elements are actually being made in this S process. You can see that in a 25 solar mass star, the impact was continued as well. It went out a little bit further, but perhaps it wasn't quite as tall in terms of how large the particular enhancement was. Here you see that nickel was significantly depleted because of this increased cross-section. And what had been going on? These were measured cross-sections. So what drove this to have such a big impact? First of all, cross-sections for the weak S process, because of this region that they are in the chart of the nuclei, tend to be small, particularly for even nuclei like nickel-62. Which makes them difficult to calculate. They're likely non-statistical, which means the theoretical tools that we have for calculating the cross-sections struggle. And individual resonances and direct capture may likely play a role. And because these cross-sections are so small, you're not in equilibrium in terms of your burning, which means that changing one cross-section affects how many seed nuclei are available for each of the following reactions. That's why you have this effect where 30 nuclei were affected by this single change. And many isotopes in this regime exhibit these small, difficult-to-measure cross-sections. Okay? So partly motivated by this, there were a series of stellar sensitivity studies that identified a range of necessary cross-sections. And so what happened over the following 15 years is that new measurements were performed in this region that really revealed that the uncertainties were much larger than people had expected. And new cross-section measurements were changing the cross-section by more than 30%. Here's a list of isotopes, and all of these were, quote, well known to 7 to 15%. Why were the measurements getting it so wrong? Largely, it has to do with the fact that there were large backgrounds that were difficult to quantify in the original measurements, many of which had been performed in the 70s and 80s. And so this series of sensitivity studies, led by Marco Pignatari and others, really motivated much of the work that happened over sort of the following 15 years. And I'll show a couple of those measurements. Here's one from a neutron capture measurement of nickel-63. Nickel-63 is interesting. It's not one of these bottleneck nuclei, but it's an unstable nucleus, so no cross-sections were available. And it really controlled the abundance of copper-63, which was being used to set how much material was being made in the weak S process. You'll remember I talked about this residual method, where it really matters that you know for these nuclei that are being attributed to the S process, we have to get it right so we can scale everything. And so this was a really big deal for nickel-63. And so increasing, improving our understanding of the cross-section here, the previous predictions, as you can sort of see down in the black line that I'm running my little hand-shaped thingy over, tell you that's sort of where it was. And then there were measurements both performed here at Los Alamos as well as at NTOF, and they increased the cross-section by almost a factor of 2. And so this means that more material is going to be captured in nickel-63, which bypasses copper-63. Okay? And so that changes how you calibrate the weak S process. Shown up here is actually the cross-section data, so you can see some of this resonance information that we can pick out. And one of the real strengths of a time-of-flight measurement is that you get really this differential information about the cross-section, which is in many ways the best type of cross-section information we can get. Copper-63 and copper-65 were both also measured and revisited. And again, what we saw there, this was a case where there had been old measurements that had been performed again, sort of the 70s and 80s. There had been new activation measurement which lowered the cross-section, but then calorimeter measurements remeasured it and brought it back up. And so there was some question with that. And again, it was in, some of the things tied up in the experimental techniques, but we've really confirmed that these larger cross-sections, which in this case actually did match the earlier results from the 70s and 80s, seem to be correct. And so here, down in the bottom red, wait a second, I've got myself lost. You can see where things have sort of landed, and the new dance results really favored some of the, the red down below, there's too many reds on this figure, I apologize for that. The red was the Jeff results, which had taken into account the activation measurements that turned out to be too low. And the red band here matches reasonably well with the earlier Bao compilation and the Tyndall results. And so this favored results from copper-63 as well. And so you can see that these increased cross-sections, again, increase the abundances of elements that are made following it, and you see that same type of trend that we saw in the nickel-62 in the copper isotopes. So these are two snapshots, but I think that in many ways the real takeaway is that the majority of the stable isotopes in this region have been revisited since 2005, and there's really been a lot of work done here. This figure is now a couple of years old, so I think that a couple of the orange boxes have turned green since then. But you can see that in this whole region between iron all the way up to here, I think it was zirconium, many of these nuclei have actually been revisited and new results are available. So we've really strengthened the state-of-the-art for measurements for the weak S process, which is an important accomplishment from the nuclear physics side. Now, we've talked a little bit about the weak S process and particular isotopes there. One of the challenges with the S process as a whole is there are a lot of isotopes on it, and so there's a lot of things that are needed. And sort of what's going on through the S process is you have a stable isotope capturing the nucleus that may then beta decay and continuing along. There are isotopes that may only be made by the S process, so understanding those is a big deal because it really ties things down. The other thing that can be exciting is you can have a nucleus that both beta decays and captures a neutron. And what this allows you to do, you have what's called a branching. If the neutron density is higher than expected in your stellar environment, you favor moving on through to your next stable nucleus. Whereas if it's lower, you favor beta decay. And so you can look at these abundances to tell you something, if you know the cross-section, about what's actually going on in the stellar environment. Okay? You need this information in multiple temperature ranges and things like that, but these branch points are particularly valuable. And so the next piece that I want to talk about is about the main S process. Now, the main S process doesn't see this propagation effect. So many of the stable, and the cross-sections tend to be larger in the main S process. And so many of the stabilizers are pretty well known, but not the branch points. Now, the main S process does not operate at the low Z range, or low A range. This is a much higher, 90 to 210, and it's in low mass AGB stars that it's predominantly moving forward. So that means 1 to 3 solar masses. And it's taking place during helium shell burning. So what does that look like from a, I will call it, at best, a bad cartoon perspective? So a low-mass AGB star, or asymptotic giant branch star, is one that's already burned all of its core hydrogen and helium, so you're left with a carbon-oxygen core. It's not really massive enough to sustain carbon or oxygen burning in the core, and so you have this core that has a little bit of helium shell burning going on the surface, and it's not even stable, and there's a thick helium shell, then you have a thin layer of hydrogen burning going on, and then a thick hydrogen shell outside of that. And there's seed material from previous nucleosynthesis episodes distributed throughout the star. But this is not a stable configuration. I've drawn it as if it is here. In fact, what's going on looks more like this, where over time, you will have a buildup that allows you to ignite neon-22 alpha N in this thin helium-burning shell that's not burning most of the time, all of a sudden ignites. It puffs the star out, is the best way that I know to describe it. And in that puffing out, it first of all makes a bunch of neutrons through neon-22 alpha N for a very short period of time. If you look, this is a scale of 200 years. So really a short time scale. But when it expands the star, then it cools everything down so the burning can no longer be sustained. And then it collapses back. In that collapse, some hydrogen is mixed down in, which allows a carbon-13 alpha N neutron source to operate. So you've got multiple different things going on here. These are operating at different temperatures in different parts of this helium shell. And then what's also sort of hidden away is this eventually quenches, and you have about a 100,000 year period before the next cycle of this happening. And a star might go through, 10 to a few tens of these types of episodes, depending on details of how the star existed. But what it means is you need temperatures over a wide range of temperatures. These two neutron sources operate at different temperatures. And the burning rates will be very different. And so this is a very dynamic environment. The advantage of a dynamic environment is we can actually say something about it with the right neutron capture cross-sections. So one thing that I'm very excited about is some particular measurements that we're looking to do here at Los Alamos on thallium-204. This is right at the end of this main S process, and in fact, it only takes place in metal-poor stars. Thallium-204 is about a 2-year half-life. Here you can see one of my colleagues, who's a radiochemist, Dash Kazamor, who's actually assembling the target that has about 10 milligrams of thallium-204 in a matrix of about 200 milligrams of thallium-203. And we're preparing this for a measurement we're going to do. You can see that these are very important collaborations for us with the people that can actually make these radioisotopes, because we've gotten to the place, and I'm going to talk about facilities coming up next, where for many of these, we can actually do the measurements if we can get a hold of the samples, and if we can make these radioactive materials to perform the measurements. And so this is a piece where we're trying to understand what are the conditions inside the star really right at the end of the S-process nucleosynthesis. And again, this only takes place in metal-poor stars, because in stars that start off with more seed material, you never make it all the way out to this sort of thallium, lead, bismuth endpoint. So why thallium? It gives us this window into old metal-poor stars. it controls the production of S-only lead-204. Again, these isotopes that can only be made in the S process are particularly valuable for telling us about how we put together these complex environments that have multiple different nucleosynthesis processes. The computation of neutron capture with beta decay gives us information about neutron densities, and then one of the oddities in the system I'll go back to and just show here in a second. Thallium-205 is stable in the laboratory, but not in a star. So in a star, thallium-205 actually decays to lead-205. And so that's why there's this double blue arrow here. So this stable element, because you're in a plasma, you open up different beta decay channels. You'll have, you basically remove some electrons to open a new decay path. And so that also gives us additional information about temperature, because what the temperature of the plasma is at tells us about the electron population. And so that's why this is pretty exciting. It's a brand new project that's just underway, so we don't have results to show on it, but this gives a feel for where new types of measurements are going in this piece of physics. Now, so I've talked a little bit about neutron-induced reactions and some of the measurements that are being done. And now I'm going to transition a bit to facilities, because these are the tools that actually allow us to do this work. I don't want to spend dive into this in great gory detail, but not surprisingly, if you want to study neutron-induced reactions, you really need some neutrons. This is hard because they're short-lived. You can't accelerate them. You can't steer them. So all of the things that you usually use for charged particle beams to get things to go where you want tend to not behave or not work for neutrons. They're difficult to trap. And so you have to make them in situ. And so neutron facilities will typically employ either a spallation reaction to make neutrons, direct reactions. I'll talk about that a little bit. There are also reactor neutrons that can be used, but I won't say very much. I won't actually say anything else about reactor facilities aside from mentioning that they can exist. So how, if you want to do a time of flight measurement, does this kind of look? So you have some sort of bunch of charged particles that comes into a target that's going to make neutrons. Here I've indicated it for a spallation source. This is, we're going to come back to this and see that it looks a lot like dance, which is why I talk about it a lot. But something happens to make neutrons. And then you literally measure their time of flight. So you have to have a pulsed beam, and then you basically collimate this beam of neutrons until you move it downstream somewhere to a sample inside of a detector. The further away you are, the better your measurement of the time of flight, and the better your measurement of the neutron energy. But the bad side is you're using collimators. So you have a 1 over r squared loss in the number of neutrons, right? And so this is sort of the trade-off that you have to make. Different facilities do these things and have different features to the details, but this is sort of the basic principle of a time of flight setup, is that you need some sort of pulse to make a set of neutrons, and then you have a white neutron bunch of many energies, and then you measure how long it takes to get to your detector, look for a signature, and that tells you the neutron energy that caused the reaction. One of the ways that this is done is with direct reactions. So lithium-7PN, you can have a pulsed proton beam. On the lithium target, it makes neutrons. This is a picture from the Karlsruhe facility from about 1997. This is actually, I was an undergraduate, I still show these slides because this is the first piece of research that was sort of real research that I got to do in nuclear physics. And so we actually measured how the neutrons behaved as a function of emission angle. And I was surprised to learn that the physics that I was learning in my undergraduate physics class could actually be used to do real physics. 1/2 mv squared is actually how you determine the neutron energy for these low energy neutrons. And then one of the cool things about the way that this setup was is when you integrate over all of these angles, you get a spectrum that looks reasonably Maxwellian, which is what's going on inside the star. And so you can measure something that actually can be directly related to what would go on in a stellar environment. Now this was, as I said, circa 1997. These same types of facilities have been significantly advanced in the last 25 years. And now the real power is in driving higher and higher intensities of proton beams to hit those lithium targets to make quite intense neutron fluxes. So for activation, you could be looking at on the order of 10 to the 12 neutrons per second. And for time of flight measurements on the order of 10 to the 7 neutrons per second. When you keep in mind that in some sense a neutron is a radioactive, it's not an ion, but a radioactive beam, you can compare this to the types of fluxes that you get from a rare isotope beam, where in many cases, if you have a beam of 10 to the 5 particles per second, you think that you have a really strong high-power beam. And you can see that these neutron beams are exceeding that by several orders of magnitude to many in the case of activation. This is sort of a picture from the Franz facility that's being built at Goethe University in Frankfurt. But the Sarah facility in Israel is also developing these capabilities and is really pushing, Saraf is even pushing, I think, up to 10 milliamps is where they're hoping to land in their proton beams. So they can really push to the most intense neutron beams. There are a wide range of neutron facilities around the world. And the only real there are a few facilities that have been shut down, like Arella or Karlsruhe or IPNS at Argonne. But what has been quite exciting to me is the number of new facilities that are coming up. So Lance and Enthoff are both places that I've worked that have been operational for over 20 years now. Same with Jelena, but Saraf is new, Franz is new, the capabilities at LBNL have been redeveloped. Notre Dame has a new capability, and Alba has been in operation for, I want to say, about 10 years. So there's sort of, I think, a renaissance of the types of facilities that are being made possible for doing these types of neutron-induced reactions. And now from here, I'm going to transition for sort of broad things to some very local things. This is a picture of the Lance Accelerator Facility here at Los Alamos. It's an overhead view. The ion source of our accelerator is all the way up here at the top, and then this is an 800 MeV proton LINAC. It's about 1 kilometer long until you get basically here where there's a switch yard and the beam is delivered to actually many different facilities. The facilities that I'm going to talk about are all over here on the left-hand side, where we have a neutron spallation target where we do these time-of-flight measurements for a couple of the facilities. But this is sort of a picture of Los Alamos on actually kind of a cloudy day. This is more of a artist's conception. So this is these actual different flight paths that we have. And so here, our proton beam hits a tungsten spallation target. We have several of those capabilities. One of them is this what's called Target 4 facility, and the other is at Target 1, which is hiding. Here it is over here. And we cover neutron energies from milli-eV all the way up to sort of tens of mega electron volts. And so there's a very wide energy range of neutrons that can be studied here at Los Alamos using these time-of-flight neutron beams. And so we take advantage of both H+ and H- beams to drive our facilities. The Lujan Center is where DANCE will be, and that is a moderated neutron source that has sort of neutrons up to about 500 keV, and the WNR facility generates neutrons at much higher energies from a few hundred keV up to a few hundred MeV. One of the features of the facility is it is truly a multi-user capability. When I first came here, it took me a while to appreciate how big of a deal this is. But for each of these little arrows that has a name on it, that's a different flight path and a different capability for doing measurements, each of those is getting on the order of 3,000 hours per year of measurement, okay? And so that means that there's a lot of work that can be done, and this comes from the fact that the neutrons go in all directions, whether you want them to or not. So you have to collimate them, and as long as you put in a collimation setup, you can have an experimental measurement capability there. And so if you compare this to how measurements might go at a charged particle facility, it's lower than many charged particle facilities. When NSCL was running, they tended to run 3,000 to 4,000 hours a year. of measurements. A good year for the Atlas facility at Argonne ranges from 5 to preferably 6,000 hours a year. So we're much lower. However, we're operating 10 instruments each at this, I say nominally 3,000 hours. Some years it's closer to 2,500, but 3,000 hours a year of measurements. And so that means that we're operating 8 instruments or 10 instruments each at this type of production level. So a lot of work can be done with these neutron facilities. Okay, so dance, the place where the measurements that I showed earlier were being done. Here we're using a barium fluoride array. So each of these colored prisms is a different piece of barium fluoride. It's a calorimeter setup, and it's a 4-pi geometry. Half of that 4-pi has been cut away, so you can sort of see. And we'll use this time of flight to measure things going on inside the detector array. For dance, we're looking at a few 10 to the 5 neutrons per lovely units that get used for this, but neutrons per second per square centimeter per energy decade. And so we can actually measure the gamma rays that come off based on a neutron capture reaction. Where we're really pushing things, both for dance, but also for our other capabilities here at LANS, are pushing towards radioisotope measurements, because this is where there are no measurements done to date, in many cases. And so while we've done stable isotopes and long-lived actinides have been the, sort of the meat of our program for a long time, there's a real opportunity for transformational measurements on unstable isotopes. And we think that we have a unique opportunity in terms of the things that we can bring together in terms of beams, detector capabilities, samples, and just sample handling expertise to address some of these directly here at Los Alamos. One of these new capabilities is an instrument we're calling DICER. And the idea here is maybe I can't surround my sample with the detector like I do with dance, because it's just too radioactive. And so instead, what we can do is measure neutron transmission. We look at the neutrons that come through, and this tells us about these resonance properties. And we use those resonance properties then to inform calculations, and when they have the resonance information, then they can actually make accurate predictions. And the advantage of this is that in transmission measurement, you can separate your detector and sample by 10 meters. In dance, the separation is about 17 centimeters. So the radiation field that your detector sees is way, way, way down. The other trick is that for transmission measurements, what matters is how long the target is, not actually its mass. So if you can make a really thin but very long target, which is what's sort of being shown down here inside this little tungsten can, you can measure transmission very well, even with a small amount of radioactive material. And so just to give an idea for this, one of the works that's being studied for DICER is particularly looking at yttrium-88. There's a whole variety of reasons that we're not going to discuss now on why yttrium, but to do a direct measurement with dance, we would need 6 orders of magnitude more neutrons because of the radiation field from yttrium. DICER can do that measurement now. The challenge is you have to really understand your alignment, because you're trying to pass a neutron beam through a tiny, tiny hole, and you have to be really sure that you've hit it right. And so a lot of work has gone into really taking advantage of advances in engineering and metrology type work to make sure that we understand the details of our measurements in quite exquisite detail. So we're trying to align a 0.1 millimeter sample over a 30-meter flight path. So that's a little bit of a challenge, but it'll open a wide range of isotopes for measurement for basic science and applied physics. Another direction we're pushing in is an instrument called LENS. LENS is looking at NP and alpha measurements, so a lot of these are more interesting at higher energies. It's not part of the neutron capture processes in the same way, but it can be important for the neutrino P process. And this capability has actually successfully done measurements on nickel-56, which has less than a 10-day half-life. So we actually made nickel-56 here at LANS, did chemical separation at the set of hot cells here at Los Alamos, and then brought the sample in for measurement and got all of this done. And obviously, if you don't have all of these co-located facilities, this becomes quite hard, because after a month, your sample is basically gone. The other thing that we're doing is we're pushing on redesigning the spallation target for Lance that's being seen by Dance and Dicer to increase the number of neutrons. So our new target gives us more neutrons at the energies we care about, in particular at keV energies. And so here in black is sort of shown what the neutron flux was or neutron production was with our old spallation target. And in red and blue are the designs of a new spallation target that was just installed last fall, which will increase that by about a factor of 10 here at 100 keV. It also increases the resolution, which is important. And why does all of this really matter? Here on the right are isotopes in red dots, the radioactive branch point isotopes for the S process. And the reach of Dance is sort of shown in orange. And so there's all of these nuclei that are just out of reach for current capabilities, but with this enhanced neutron target, we should really be opening up many more isotopes that we can actually do direct measurements on. Okay? So this increase in the neutron flux, it actually does two things. One, it makes some of them easier to reach, and it means that these ones that are just below the line, we can actually measure better without challenging the instruments at the same level. Okay, so those are sort of the traditional ideas. The other idea we're working on at Lance is something really, I think, revolutionary. And this is, for the longest time, people have said, well, you can't make a neutron target, so because the neutrons all decay away. But about 5 years ago, René Reifert and some colleagues published a concept where they said, well, maybe you can make a neutron target. What if we trap the neutrons in a ball and then pass charged particles through them like you do at a storage ring? The storage ring allows you to reuse radioactive isotopes over and over again because when they don't react, they just come back again for another round. Could you trap enough neutrons here and basically make a low-energy neutron gas to make this work? It combines a spallation target, which Lance already has, a storage ring, which we don't have a charged particle. We have a proton storage ring, so we have some experience there, but not with doing heavy ions, and ISOL eventually. But the thing is, spallation target, storage ring, and ISOL are all technologies that have been developed and people know how to make them work. Lance has the proton beams to make it feasible. There's a whole range of reaction channels that can be studied. And we've looked at the feasibility and understanding the technology, and the answer is we think that there's real ways to do this. And at present, there's not another way to determine cross-sections at the less than 10% uncertainty level for some of these short-lived nuclei. And so this, if we build it, would be a very exciting capability. And what it would allow us to do is actually reach, I focused on measurements we're doing for the S process. This is sort of revisiting a slide from the very beginning of my talk. But neutron capture is basically unmeasured for the R process. That's why we have to determine our abundances based on doing S process stuff and subtracting things off. This would allow us to really reach into these R process environments and provide direct data. Further, since about 2010, a fair amount of theoretical work has gone in to show that, in fact, the R process environments really do need individual neutron capture cross-sections, and that changes in those cross-sections change the abundances that come out. Before 2010, it was largely thought that you could just get away with masses and the mass differences would tell you the whole story. It looks like that's not the case. A neutron target facility would actually enable direct measurement for neutron capture lifetimes of certainly minutes. We may be able to push down to seconds. So this is really an exciting capability. Okay, I said this is a ways off. So what can we do in terms of first measurements? And so we're developing the capability now and trying to put together proposals to actually test the basic concept of passing a charged particle beam through a neutron gas and looking at neutron capture take place. We think that we can do that with our existing capabilities here at Lance. And so we're building up that as something that we hope to deliver on in the next 5 years. And the idea is we'll produce a neutron field in the moderator, and we'll measure an actual neutron capture cross-section in a case where we already know the answer. And we'll look for this change from on and off resonance by changing the beam energy, which would say that our concept of a neutron gas really does work. And it tests neutron production, beam transport, the concept of the beam carrying the energy, and we think that we could get this for a favorable case at the level of events per day detection. And one of the other nice things about this concept is as we're moving towards a neutron target facility, as we develop each technology, there's an advantage in science that we can address with it as we're moving forward. Okay, so that sort of brings me to the end of this sort of whirlwind tour of both what type of science we're delivering and what the instruments that are enabling that are for neutron type work. And I'd say the major advances have been made in improving neutron capture rates for the weak-S process. Coupling them to stellar simulations is really key to understanding where the next opportunities lie. We would not have done the work on basically across the weak-S process if some of these really key sensitivity studies hadn't been performed to motivate those measurements. There are new capabilities being stood up for performing measurements, particularly on unstable isotopes. I've talked a fair amount about the things that are being done here at Lance, but that's not the only place. It's going on around the world. And a neutron target facility really would be transformational in terms of how we approach this. And this work really drives our understanding both of the origins of the elements as well as the astrophysical environments and processes that make them. And with that, I'll give you a snapshot of the night sky from Los Alamos, and thank you very much for your attention.